Hi folks, thanks for coming to our talk. My name is Alistair Owens and my co-presenter here is Andrei Dukuni. So we're developers at Amazon Web Services and we work on Amazon's relational database service. So one of our major duties is maintaining the Postgres databases that actually manage the core of our services data. And we're going to take you through the work involved with that this afternoon. So our talk's going to begin with a little bit of background on our service and how we reach kind of a position of long-term scalability. And from there, we're going to go through and talk, how we, the work that we perform to keep the performance of the database stable, along with some lessons on the handling of both the database and how we develop the applications that talk to the database as well. And finally, we're going to go through some of the wishes that we have for the future that, if they were implemented, would make our lives significantly easier. So I imagine many of you in the audience are familiar with RDS, but for those of you that aren't, we're a service that manages relational database systems on behalf of our customers. So RDS builds out our services in independent regional units, and at the heart of each of these units is a Postgres database that stores the kind of the service metadata and so on. An interesting wrinkle here is that actually one of those customers is ourselves. So the Postgres, the metadata database is actually an RDS database that's owned by the region that it runs. So the core of RDS is a fairly classic service architecture that's existed since the early days of the service. So we've got like an asynchronous front-end web service and a synchronous front-end web service and an asynchronous worker. These components have got direct access to our metadata database. As the service has grown, we've obviously expanded our internal service ecosystem as well. But these don't tend to have like direct access to the database. They're mediated via like service interfaces. But the core of the service still has a lot of work to do for us. So a couple of minutes ago, I mentioned that our metadata database is actually an RDS instance. Compared to building our own management system outside of RDS, this gives us an awful lot of confidence in the infrastructure that we have. So in particular, kind of the regular day-to-day stuff, the sort of the backups, the monitoring, the failover, those kind of things. They've had gotchas worked out over the course of well over a decade at this point, and they're as a result they're pretty rock solid. And we like it because it allows us to work with infrastructure as RDS developers that we're familiar with as well. There's a limitation of this approach though, which is that any RDS operations that involve taking the database down for any length of time, well they'll stop working basically in this environment. So because when the database isn't running, the rest of RDS won't be able to perform. So we can't use any internal automations that trigger database downtime, and this kind of has implications for recovery as well. So our multi-AZ failover, the standard kind of failover mechanism that we have in RDS, that's architected to work independently of the database, so we can rely on that. But more complex recovery operations won't work. So in order to combat this, we've implemented a separate kind of recovery service that looks after this database and kind of fills in the holes there. So, sorry, I was a little bit late on that one. So yeah, overall, this approach has been a big win for us. I mean, the particular advantage is that the confidence that we get in our day-to-day operations, and particularly only having to kind of cover, testing-wise, only having to cover the self-hosting functionality, kind of radically reduces our test scope. So it's very helpful. So let's get into some kind of broad numbers. For us to say, in our largest regions, the core metadata database runs at well into the hundreds of thousands of transactions per second on the primary node, that is. So the primary node is pretty busy. We try to minimize our read I/O. We'll go through phases where that starts to grow a bit, which we then resolve via optimizations or scaling. So, our working set is typically mostly in memory. But the workload is mixed. So while the majority of it is pretty straightforward, we do have a good chunk of more complex queries that have like non-trivial runtimes. A big thing to emphasize from an operational perspective is that for us, any significant interruption of the service it's a big deal. So we don't really have the ability to say, oh, okay, we'll fix that in some quiet period, because there aren't really any true quiet periods that we can rely on. So these numbers are reasonably large, and the most interesting thing from our perspective is that they continue to grow. So a large driver of this growth is just additional customers who create more instances. But we do see growth as well as a result of customers choosing kind of increasingly automated options. That the automation tends to hit our APIs more heavily and drive more work as a result. So over time, in order to keep the service stable, we've gone through many cycles of query optimizations. But as you knock off the top hitters, the bang for your buck starts to go down. The probability of any regression and its performance impact kind of increases somewhat over time as well as you grow and as you optimize more. So as the tables grow, like a de-optimization that triggers, say, a table scan or a full index scan or so on, it becomes more impactful. As the query counts grow, a de-optimization in the query plan becomes more likely to flatten your database again because there's just more of them. There's more of them running, and increasingly, like connection depletion as well becomes a bigger risk. So at the infrastructure level, we can kind of keep scaling a long way by using read replicas and caching, right? These are pretty standard mechanisms, and they're immensely effective. But they do introduce kind of some points of unreliability in your system as well. So particularly like code that was designed for kind of read your own writes consistency can appear to be working correctly under normal service conditions, but then when you start to experience latency, you can get non-obvious and potentially pretty damaging bugs as a result. And caches have similar concerns with the additional fact that they can be hard to keep in sync and so on, and particularly that they can be hard to repopulate on service restart events. So yeah, for our purposes, we found building on top of a relational database has been very flexible and really great for productivity. But it does start to get more challenging to maintain stability as you grow. So what we've moved towards is a kind of a sharded model. Effectively. So the great thing about this is we can put a cap on our maximum shard size and thus address vertical scaling challenges. So we get that same flexibility that we've enjoyed from relational databases without this kind of flakiness that gets introduced as you scale up. So yeah, so this is what we've done to reach a kind of a largely horizontally scalable state to ensure we're in the clear in the long term. I'm going to hand over to Andre to talk over some of the mechanisms that we've used to scale as we approach that infrastructure.
Thank you, Alistair. Hi everyone, once more, and my name is Andre, and I will walk you through our performance management story, and I'll also share with you part of our patching story. So in our system, we focus on maximizing scalability and maximizing predictability. We want to have a very reliable and very beautiful system. That is why we always watch for 3 bottlenecks, for CPU, for IOPS, and for memory that is available for the instance. So on this slide, you can see the techniques that we use to manage our performance. And in the next slides, I will share our special consideration to follow them. But before we can start talking about managing the performance, we need to establish monitoring for the system. Okay, so because our databases are Amazon RDS instances, it comes with basic health metrics. It provides us CPU, IOPS, database latencies, free storage, and also it gives us an ability to look at Postgres logs, which is another very useful source of data. However, we also rely on other source of monitoring. For example, we extensively use Amazon RDS Performance Insights. It gives us an ability to zoom out or zoom in into
particular local events or to zoom out into historical trends. It also gives us an ability to slice by database weight events, by SQLs, by users. It's very useful for any kind of debugging and investigations. In addition, we also heavily rely on PG statements. It gives us unaggregated stats for most of our SQLs. And the main thing here is that it can give us the list of queries that run the most frequently on our databases, or the queries that Postgres is waiting the most time running them. And these are the obvious candidates for optimizations. So this is how we look at our database from database perspective, but we also want to look from application perspective. So we have continuous profiling on our applications. It gives us an ability to look at database latencies, and it provides us a comprehensive history. And from another benefit, it sometimes can help us identify issues which are hard to identify from database side. For example, extra overhead for frequent connection validations. And the last but not least, we have an ability to log our SQLs. We log them with timing and with redacted parameters. We use that for performance testing, which I will talk about in patching section. And also it gives us an opportunity to test any slow queries. We can use them, we can try to optimize them, and actually confirm that some optimization will give us some results. And also it is very helpful in some situations like deadlocks. We can find the queries that cause the deadlock and move from here. Okay, so now once we established our monitoring, we can start optimizations. So as I mentioned, the two obvious candidates for optimizing are queries that Postgres is spending the most time running them, or the queries that have very high frequency of execution. The thing with high frequency queries is that we notice that they can drive non-obvious performance implications. For example, locking contention or CPU exhaustion. I will talk about it in a bit more details in a few slides. And so how do we deal with that? Obviously, we have indexes, and indexes help with almost everything, right? We also try to use partial indexes as much as possible. It allows Postgres to filter out a bunch of rows, and we can more efficiently query only a subset of the data. We use partitioning for the tables that we can partition. It not only allows Postgres to query less data, but also it helps us to reduce maintenance overhead because vacuum becomes less aggressive. And is it enough? Because we want to have a predictable system? Well, not really. So we still see performance cliffs, and Postgres still tends to use not the best query plans. It can flip query plans quite often, and it results in some changes in our metrics. We should also watch out for input-output. For example, IOPS metrics, because sometimes if Postgres does not have enough memory for its cache, it starts reading more often from disk, and it drives IOPS, and it can have an impact on application latencies. And locking contention, we'll talk about it in a second. Okay, so we want to have a predictable system. So how do we do that? So we prefer to have simple queries instead of having complex queries. That means that we don't want to squeeze the maximal performance out of the Postgres. We want it to be predictable and that it will run efficiently in most of the use cases. So a simple example here would be that we prefer to split complex queries into few simpler ones, because that way Postgres is able to run them more efficiently and in a more predictable way. That also means that our average performance might be slightly slower, mostly because, for example, in this use case, when we split queries, we will get network overhead for round trips. But it also means that the system is more predictable, and if it is, then that's what we want. And the race for predictability also means that we don't want to have extensive use of custom statistics, or for example, PG and plan. It does not mean we don't use it, but we try not to rely on it as much as possible. Another motivation here is that we have many developers that contribute to our system, that create new queries, that update existing queries. And this process with that many people who work in the system is hard to properly overview. So the process when we want to review these queries and to support any performance changes it does not scale very well. So that's why we want to have these rules when we want to have simple queries instead of complex ones. And that way we enable development and we make our database predictable. Right, I mentioned a few times about lock-in contention. So in a natural evolution of our system, we got a few tables that became heavily indexed and that have very frequent access to them. So it happened to drive some non-obvious lock-in contention because once you have many indexes, any access to these tables will go through slow path for acquiring lock for them. It will result in lightweight locks wait events. And as we learned after our recent upgrade some time ago from Postgres 10 to Postgres 6, from Postgres 10 to Postgres 14, I've been hearing about Postgres 17 quite a lot, so now I've forgotten what version we're running. So once we upgraded to Postgres 14, these lightweight locks events, they became more spiky. And it happened to be a no issue because Postgres on newer versions had a quadratic behavior with handling these lightweight locks lists. And the thing is that this issue was recently patched in Postgres 16. Also, Postgres hackers kindly backpatched Postgres 14 version. And once we upgraded our databases, we saw the significant improvement in our lock rates, and also it improved our latencies for applications. All right, bloat. So bloat is another natural process for Postgres that happens for us as well. We have indexes that could be quite bloated, and that's how we manage it. So we have auto vacuum for all tables. We make sure that if tables, for example, have very quick growth, or if they behave as queues, then vacuum may not be as efficient for them. So make sure that we run the vacuum for them as often as possible, so it helps with the overall health of the system. And also partitioning. An obvious win here is that when we partition table, we can set the retention policy for all partitions. It helps vacuum, it helps Postgres. So recommend doing that. And we also do periodic maintenance. So we rebuild our indexes when needed. We have PGPack in our inventory, and we also run vacuum full. But we only run vacuum full in situations when we can do that. For example, in major version upgrade. So I will mention that in a few slides as well. Cool, caching, okay. So we have caching, obviously, and it usually always drives performance improvements. But we have some rules that we apply here. We want to have request level caches or small shared caches. The main motivation here is that in case of deployment of the application or the recovery of application, we want to be sure that the cache could be refreshed very quickly and without any impact to the system. And we also prefer to cache data which does not change too often. And replicas. We have a few of them. We even have some redundancy here. So we have replicas for some sort of horizontal scale here. We offload some read-only traffic to these replicas, but we only offload traffic that can tolerate eventual consistency. And we also have replicas that we use for recovery from disaster scenarios. For example, if primary node here is unavailable for some reason, we can promote the promotion target here. It will be serving the traffic, and it will become a new primary. And you can see here that this promotion target replica, it has change replicas of its own. So if we need to promote this promotion target, these change replicas will be new read-only replicas that will be serving read-only traffic. Okay. Now let's briefly talk about patching. I will focus on major version upgrade because it's the most interesting one. I'll try to be quick and major version rate was already mentioned in a few talks, and it will correlate with our as well. So for major version rate, we use logical replication. So we establish logical replica, and we create it using the approach that we call Amazon RDS snapshot approach, but we also refer to this approach as Instacart approach, because they were the first who suggested to create logical replicas that way and use it for major version grade. So we use this approach, which I will expand on in a bit in the next slide, because it does not have any impact on vacuum health for the instance, in opposite to the approach when we create logical replica and we need to copy the entire data from publisher to subscriber. Given that said, this approach, which we call RDS snapshot approach, it's kind of not officially supported by Postgres. And that is why we want to have comprehensive validation in our pipeline. So we want to make sure that replicas that we create, they will contain exactly the same data as our publisher, and we won't cause any data loss. And we also use this opportunity to perform database maintenance, kind of maintenance that we would not risk to run against active system, like running vacuum full and other operations. Okay, so this is our standard RDS setup. We have our primary, we call it source here, and it has a set of replicas. Traffic goes to this primary node. So we want to create logical replica of this source primary instance sitting on lower major version, which is Postgres 10 in that case. So what we do, we create the replication slot on this source instance, then we take an RDS snapshot, then we restore this RDS snapshot, and this restored RDS snapshot, it's here target instance, and then we continue logical replication from the moment of time when the snapshot was created. So now we only copy data changes that happened after snapshot was created and until now. Okay. And then we create the same set of replicas for this target instance. I didn't mention that, but yeah, like our target instance here uses higher major version. So we create logical replica, we upgrade it, we establish logical replication. Then we create replicas, so now this cluster has new version. And then we repeat the same process and create another set of databases here, which are sitting on lower version. So we can use this for rollback from newer major version if needed. Right. So now, once we have all these three databases established and logical replication running, we can use this opportunity to do some maintenance. We can run vacuum full, we can change types of our columns, we can create new indexes, add new columns, anything that might take some time. And I mentioned about comprehensive validation that we want to do to ensure that data is consistent. So here in this setup, you can see that we have special validation replicas. So we use these replicas to calculate hashes of each table in all three databases. In order to do that, we need to freeze them. So what we do, we stop replication in all these three validation replicas at the moment of time when all three of them have exactly the same logical sequence number. So now when they are frozen, we can calculate hashes, the data is not changing, and we can make a decision if data is consistent or not. Once it's consistent, we can move on. We need to sync our Postgres instances. We need to warm our target database, and we are ready to cut over. And we can switch traffic. Major version rate is done. Okay. Right. So I said that a few times already. We want to have predictable system, right? So even for major version grade, which we usually expect to bring some performance improvements, we want to know in advance what performance improvements we'll get. So we do performance testing. And to do that, we use this comprehensive SQL log with timing that we can get from our applications. So these logs, these SQLs, they have timings when they were run on our databases. So we can get these SQLs, we can simulate the process when we apply these SQLs to test instances, and then we can compare results. So what we do, we capture some load, then we create 2 instances, one instance on lower version, on our current major version, then we create another instance with target major version, then we apply this load to both of them, and then we compare results. So for example, for our most recent major upgrade from Postgres 10 to Postgres 14, this tool gave us a prediction of getting 10–12% of relative improvement, namely CPU reduction. And as a result, after actual upgrade, we saw 13% of CPU decrease. And also because we used this opportunity to rebuild our indexes to run vacuum full, we saw a significant increase in read IOPS. So this major version upgrade is always gives this opportunity to run some maintenance, and everybody should use it. Okay, that concludes my part, and I invite Eliezer back.
Thanks, Andrew. So a notable thing about our experience with Postgres is that we need to kind of understand and cooperate with our consuming applications in order to ensure that the database remains stable. It's not something where we can just kind of say, here's some access to the database, go wild. So a lot of this comes down to 2 factors, like management of active connections and general query performance management. So connection depletion is a really common source of availability challenges. And we address this by a few basic database measures to begin with, like statement timeouts, idling transaction timeouts, log timeouts, all of the basics there. And also primarily by application level mechanisms. So the most important thing for us here is to avoid network calls while we're inside transactions. This is because if we're in an active transaction, the connection is consumed. So if a connected service starts to run slowly, then we will find that we'll have a pile up of consumed connections, and effectively we'll have then functional unavailability at that point. This is one of the reasons why just using a connection pool isn't just it's not a panacea to sort of connection-related woes. With a connection pool, you can get yourself using a smaller number of connections in the in the general case, but when you hit these kind of edge cases, you may find that it actually makes the connection depletion problem worse. But sometimes avoiding calls to other services while you're inside a transaction is impractical. For these cases, like one solid option for us to use is circuit breaking. So circuit breaking is a thing that you can apply to your service clients, which maintains some kind of application level state around the latency and failure rate of calls from that client. And it allows you to temporarily fail fast on that client if you go over certain thresholds. So this is useful to prevent like one bad workload from consuming all of your resources, like connections or application thread pools or whatever, and then trashing a bunch of unrelated workloads that don't even need access to that client. So the workload will fail, but it won't take everything with it. So along these lines, it's also advisable to implement mechanisms to limit pool consumption for different workloads as well. This is another mechanism where you can say, well, if one workload goes down, it doesn't completely destroy your service. When it comes to performance management, we have 2 main strategies. Firstly, just to watch pretty aggressively for significant changes in query performance, which may be triggered by application level changes, or it might be data distribution changes as well. So our preferred strategy when we have an unreliable query that changes plan frequently, as Andrew mentioned, tends to be to rewrite it to make it a little bit more obvious for the optimizer. This tends to require a little less expertise from the application developers. The other thing here is that because in some places the code changes rapidly, places where we've added, say, statistics to support a certain query and so on, it can get a little bit challenging to track, do we still need those or not? I'm going to come through to operational reliability now. So this most particularly relates through to schema changes, which is something we have to watch pretty carefully. So the thing is that any kind of long-held aggressive lock is likely to cause availability impact for the entire service as a result of connection depletion. So we carefully manage the kinds of schema changes that we're allowed to make. It's metadata-only changes or ones that don't apply very aggressive locks. And in particular, we pretty much have to avoid transactional DDL, unfortunately, and many changes that we make, we have to apply in kind of a multi-step manner to minimize the amount of time that aggressive locks are taken for. So we watch this pretty carefully. Beyond the expert review that we apply for each of those those changes, we also have some tests that try to catch any changes that would take long-held locks. The other thing that we do here is that as we're rolling out a change, we have automation that monitors the rollout and kills any workload that conflicts with the schema change. So our workload is, our regular service workload is architected to be retriable. So this is a solid strategy for us. Like the impact of killing a little bit of workload to push the schema change through is much lower than it is to just wait for the lock and have connection depletion as a result. So I think one thing that's not obvious to all the developers that we've worked with in RDS with this is that even these dictionary-only schema changes can cause an impact to service availability. So this is because if any workload blocks acquisition of a table lock, all new workload on the table waits behind that lock. So if you look at this session above, you can see we've got like a long-running just select statement. We then perform an alter table where we have a lock wait on the table that the long-running select is operating on. This table then, this table level lock that's being taken by the alter table then blocks all access to the table behind that. So just one long-running, innocuous-looking select can then cause a service outage if you aren't careful with your schema change. So various timeouts being applied and our slow query kill automation kind of insulates us from the worst impact of this, but we do still feel the need to kind of watch schema application pretty carefully. And vacuum management is a standard topic here, and it's obviously a big deal for us as well. And so we alarm pretty carefully on the basics like transaction ID exhaustion and so on. And we try to keep the very worst case transaction age below 5 minutes. This helps prevent excessive bloat, which leads to worse performance in our system. We used to have an exception here, which was for taking PG dumps. So we take frequent logical backups just to give ourselves an extra measure against corruptions, basically. And on some of our larger tables, this could some of our tables are relatively large, and as a result, the dump can take hours in some cases. So we wanted to move this out to a replica, but if replica feedback was off, the PG dump queries would end up getting cancelled, and if it's on the vacuum, still applies and still hurts us. So what we did was create a dedicated dump replica, which in a similar technique to what Andrew mentioned for the major version upgrade, we just pause replication prior to taking a dump. Finally, I wanted to come to our wish list of things that we would love to see in Postgres and that would make our lives better. I think the background to which we're coming to this with is that for our purposes, like running a kind of interactive application on top of the database, like the feature set of Postgres is for most cases more than adequate for our needs. Where we tend to experience more concern is around operational predictability. So I think in particular, we want to be safe from rapid changes coming both from the database side and to be able to insulate applications from each other some more as well. So kind of safe from the database side and from the application kind of attacking the database, as it were. So, I mean, I think the two single biggest improvements that we could see here is some much more extensive like resource consumption limitations per user. Right now we have the ability to limit by, say, the number of connections. We'd love to, be able to apply kind of like CPU or IO level limits there as well. And some kind of query plan stability implementation just to rid us of this fear of major swings in query performance at an unpredictable time. Beyond this, logical replication that, say, replicates DDL and so on would be nice. Something that just allows us to easily just run permanent logical replicas in production, giving us more insulation against potential physical corruptions and so on. We'd also see the things that we've done to make schema changes safer. We'd love to see some kind of actual solution for that inside Postgres as well, like mechanisms to, say, have DDL rollback changes that are competing with the change, and some mechanism maybe to disallow any changes that aren't dictionary only changes. So kind of things that keep us safe from ourselves in that case. Yeah, so I mean, essentially what we want here is to be able to give our customers, which is the RDS developers, kind of a safe and reliable environment so that they don't have to worry too much that they're going to break workloads that to them are unrelated by other applications. And we want to reduce the need for expert level oversight over the changes that they make and reduce the amount of cooperation that's currently necessary. On the performance side, I think the single biggest improvement that we'd love to see is better connection count tolerance. So we got a lot of improvements in that in the PG10 to PG14 upgrade, which was great, and yeah, just more would be lovely. We've talked through earlier about how just using a pool isn't an answer on its own. Obviously, it's advantageous, but it's just being able to have more connections is preferable if it would be possible. And beyond this, we've got some lower level importance items. So we'd love to have a native PG dump solution for multi-threads per table on the dump. I know there's sort of custom solutions out there for that, but yeah, having it in the core would be nice. And incremental materialized view refresh. I think that's a common ask, but yeah, it would be beneficial for us as well. Finally, a few minor items for operational insight. One that would be really nice for us is improvements to PG stat statements that make it easier to track changes in query performance over time. So, for example, partitioning it on, say, a daily or hourly or whatever basis. Obviously, you can simulate this by resetting it and storing the information elsewhere, but having it inside the database would be very convenient. We also love some more logging options for queries that generate excessive workload in the system, queries that appear to be driving excessive number of row count changes and so on. That would be kind of helpful for us. And finally, as Andrej mentioned, that we do some pretty extensive kind of client-side SQL logging now, which really helps when we get a deadlock situation. But it would be, nice to have that more information, more actionable information in the Postgres logs for deadlocks as well. Yeah, that's about it. Thank you.
On your wish list, you had lots of really hard wishes.
Yeah.
But there was one easy one, which was transaction timeouts, and they're in Postgres 17.
Oh, amazing. Thank you.
I mean, I didn't work on that. It's just someone did that. Yeah. Right.
Yeah, I figured the reason a lot of them haven't been done yet is presumably they're incredibly difficult. But
So do you think now that you have this qualified process, you'll wait another 4 versions to upgrade, or do you think?
I think 17 is looking quite. Andrej and I were just talking. 17 looks quite attractive, for us. So yeah, that's probably our.
Just 3.
Yep. Maybe go down to 2 next time.
They're just gonna run extended support.
Did I see that you're locked to a minor release?
No, we we perform minor upgrades as like.
Because you said you went from like 10.11 to 14.2. And that's why I thought maybe there was a minor release lock.
No, I mean, we don't love doing, we upgrade obviously as necessary, particularly for like if there's a relevant security change and so on. We don't love doing upgrades because even with a logical replication-based solution, there's still this, this period of downtime which we prefer to avoid. But yeah. Thanks, everyone.